So first I want to apologize for the Zoom technology issues this morning. I'm hoping that this will not be a common thing this semester. So I'm going to go back through lesson 1 a little bit, make sure we all start off on the same page. And then if you have any questions, please just email me or bring the questions to class on Wednesday, because we're going to pick up on this lesson. So the first thing we did was we reviewed the 4 postulates of the kinetic molecular theory that we saw last semester with gases in chapter 9. Now we're picking up in chapter 10, but as we transition from gases to discussing liquids and solids, we want to remind ourselves of some things that we learned about gases that are still true about liquids and solids, and then recognize how they are different. So the 4 postulates you see here are that molecules in a gas are going to be spread out by a distance that's much greater than their own size. So meaning gas molecules are very tiny, but they're going to be farther apart from each other in a distance that's greater than the distance of the actual molecule. This can be considered to give them mass, but because of that, they occupy no volume. Remember, their volume is going to be the volume of the container that they're contained in, which we discussed early in chapter 1, is not true about liquids and solids as much. Liquids are going to have a volume that's constant, and solids are going to have a volume that's constant. While liquids are going to adopt the shape of their container, solids are going to have a fixed shape. So just some review of that chapter 1 material. The second postulate is that gas molecules constantly move in random directions and they frequently collide. And these collisions are perfectly elastic, which means that they're going to return to their shape after the collision. An inelastic collision is like a plastic water bottle, where you crush the water bottle and you don't really ever get it back to that water bottle shape. Even if you try, it's going to be not the same. So because of these collisions are elastic, energy can be transferred between molecules, but the total energy of the system is going to remain constant. Now here's a little drawing of a gas molecule going through collisions, and each time the direction changes, that is going to be an example of a collision, either 2 gas molecules colliding with each other or colliding with the wall of the container. The third is that gas molecules exert neither an attractive nor repulsive force on one another. Now we discussed that there was ideal and real gases, and that we assume this to be true in ideal gas behavior, but real gases behave real, and there is some amount of attractive or repulsive force, but for the most part we pretended that they just did not have any sort of attraction or repulsion. This is not going to be true about liquids and solids. In fact, attractive forces is going to be what holds the liquid or the solid together. So in liquids and solids, we're going to see that the fact that number 3 is not true is what allows us to have shape, a fixed shape with liquids and solids. The average kinetic energy of all the molecules is directly proportional to the temperature. So we said that as the temperature increases, the kinetic energy increases and the motion of the molecules becomes faster, velocity. Now, this still is going to be true about liquids and solids. As we boil a liquid or as we melt a solid, as we increase the temperature of the sample, the kinetic energy is going to increase, and that's going to contribute to a phase change, which we're going to see in this chapter. So today we are going to begin our discussion of liquids and solids. In fact, we already began that discussion. How have you seen that they differ from the statements above? Well, obviously gas molecules have no attractive or repulsive forces, but we discussed that liquids and solids do. It's why we're not able to walk through walls, because that attraction between solid molecules or molecules that contribute to a solid are so strong that we don't overcome that force enough to walk through the wall. With liquids, they are going to have attractive forces like water. The beating of water and individual drops coming together to form bigger drops is an example of an attractive force. And we're going to talk about repulsive forces that we see as well, typically in our liquids. So then we started talking about Coulomb's law, and this is where we started to have a little bit of an issue with the technology. So Coulomb's law is actually a physics concept, but we're going to use this concept to describe the strength of the forces we see occurring between molecules, which is kind of the same way that Coulomb's law is used in physics, but it typically falls in electricity and magnetism and gravitational forces between like the sun or the earth and the moon. That's an example of an attractive force, which is not Coulomb's law, but it's Newton's universal law of gravitation, which mathematically looks very similar to the formula we see right here. Okay, so one of the primary differences we see between gases and the liquids and solids that we're discussing is that we have a presence of what's called intermolecular forces. So if we think about what these words mean, inter always means between. So these are going to be forces that occur between molecules. Now, the key is that these molecules must be in the same substance. And so that's not saying that they are the same molecule. They don't have to be water and water. It could be water and salt. The key is that they must be in a solution. And remember, solutions can be liquids or solids. We can take two metals and make an alloy like brass, and that's a solution. That's a mixture of two different metals, even though it is a solid. So we're going to have 4 different types of intermolecular forces, and these are so important to know. You are going to need to be able to identify their definition and then also identify when two substances have or don't have a specific type of intermolecular force. So let's talk about another type of force, which is called intramolecular. So intra is going to be within a molecule. Okay, so within a molecule is going to be our covalent and ionic bonding. These occur within a molecule, within a single molecule. Inter is going to be between two different molecules. So it's the same type of correlation to communication. Intrapersonal is within yourself. Interpersonal is within two parties, two people, how they communicate. And when we're talking about forces between and within, we're going to use the same terms, the same prefixes to describe who it's occurring between. So last semester, we spent a lot of time talking about ionic and covalent bonding, especially near the end. And so that's still going to carry over and continue to be important in our discussions, except now when we discuss when we discuss liquids and solids, we're going to add another layer, which is our intermolecular forces. And we're going to have 4 kinds: ion, dipole, 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 dispersions, and hydrogen bonding. And those are the 4 intermolecular. So we're still going to have ionic and covalent bonding, but they're classified in a different way because they're occurring between 2 atoms and not between 2 molecules. So the last thing we started to discuss, and where we'll kind of pick up on Wednesday, is the formula that Coulomb's law brings to the table. It's going to have a constant, which we don't really need to consider, and how it affects the energy because it's a constant. We're going to have charges and a distance variable. And what we see is that if you remember back to ionic and covalent bonding, we discussed that opposite charges attract, like charges repel. So an attractive force is going to occur between a positive and a negative. Repulsive forces are going to be 2 positives or 2 negatives. It's still a type of force, but instead of holding 2 substances together or holding 2 molecules together in a substance, a repulsive force is actually going to cause 2 things to not want to mix. So this is going to be our immiscible solutions, oil and water. That's an example of where you have a repulsive force because they don't have the strong attraction that we would when we have a miscible solution. So what we're going to pick up with on Wednesday is how these variables impact E, the overall attraction, how strong it is, which goes right back into this. So we're going to stop here because that's really where I started to find that the technology was not working. The only thing that we also reviewed was ionic and covalent compounds, what they are made up of. And so I just want to remind you that it was the metal and non-metal, and non-metal, non-metal. Okay? And then hopefully this will get us all on the same page. I hope that this wasn't too long to make sure you have the notes filled in. Remember that I will bring a copy of the Chapter 10 notes for you guys so that you'll have them look just like this. And we'll start on Wednesday with our Chem 1311 post test. And then we'll pick up with Lesson 1 notes.